So, good you could all make it. I hope the studying is going well. I've got everything posted now, including the homework that you did for Friday, which took me like 10 minutes to grade. It was so nice. The average was like 19.5 out of 20. It was very computational, and you guys obviously know how to calculate coordinate vectors and matrix representations. So that's good. And pretty much that's what the test is going to go up through. I posted a sample test, which hopefully if you haven't tried it yet, you might give that a shot sometime today and look over the solutions afterwards. I wrote that for an hour and 15-minute class as well, so it's about the right length of time. The one thing that I think it might have had in it is true-false items. So I'm not going to ask you like tricky true-false questions, right? I might make a statement, say this is true, explain it, or here's a statement that's false, give me a counterexample, but I won't ask you tricky true-false questions that are really hard to think about on the fly. Now that doesn't mean that, so if I say, is this a basis, right, that's kind of like true-false too, because that's yes-no, but that's more standard process that you go through to decide, so I don't consider that like a tricky true-false question. So sometimes you can phrase, certain things get phrased as yes or no, right, but you go through a pretty standard process, so it's not that surprising what you're being expected to do.
But things like that where you ask, is this a basis, and then do we have to state specific theorem names, or can we just explain the theorem that we know?
You can, if you know a specific name like rank nullity theorem or something like that, you can certainly refer to that. Or you can just say, or if it's some informal name like Annan's consequences that we talked about, you can also refer to that. If you happen to know a theorem number in the book, you can cite a theorem number out of the book, or you can just say, by a theorem from class. I don't want you saying something like, oh, by theorem such and such in chapter 5, which we haven't even talked about, something is true. Okay, it's unlikely that would come up. But just make sure if you're citing theorems that are from the book, they should be based around the material that we've actually covered. Okay, so that's why I always think that you should view your lecture notes as the first line of the material, because the book has more in it than what we actually did, and so I don't really like it too much when people start referring to a whole bunch of stuff we didn't even talk about as if it's just, just writing it down. So I'd prefer to have you stick to the core of what we covered. But yeah, you don't have to remember the number. So you can, because that's really not relevant. You could just say, by a theorem from class, or by a theorem from chapter 1, or whatever. Okay? Just make sure it really was a theorem from class, because I was there every single time so far. I didn't miss one yet. Okay, so that's that. Basically the review packet goes over all the concepts that you need to know. So I don't think I'm going to bother you too much with that. I just want to dive into a bunch of problems here. And I'm going to be grabbing these from other exams that I've given for this class in the past, as well as just some other random things that I didn't get to. For example, on this past Wednesday, I had a couple problems I was going to have you address with me really quickly at the beginning, and then I forgot to bring them to class. So I may as well do them now. So this is, I would almost call this warm-up, but I'll try and number these problems a little bit in terms of helping you keep track of where we are in the notes. So these are good. These first ones, there's really just two parts here to this first problem, and they're both pretty quick. So here's the first one. It says prove if T goes from P7 of R to M2 by 3 of R, show the nullity of T is at least 2. Okay, so this would be a nice warm-up. I've used it in the past in the group work for this class, and just didn't get around to it this time. Okay. So does anybody have any, do any bells go off? Do you start thinking about anything in particular when you see that kind of problem? Davey?
Since we're showing that the nullity of T is greater than or equal to, can we just show that the dimension of
So I know what the dimensions of these are.
Right, so the rank nullity theorem doesn't say that the nullity of that plus the rank has to equal the dimension.
Tell you what, let's slow down a little bit. Don't try and solve the whole problem. Let's just say the rank nullity theorem seems relevant here. So let's just write down what that theorem says. So the rank nullity theorem would tell us that the rank of T plus the nullity of T equals what?
Dimension.
The dimension of the input space, the domain, so that would be the dimension. We usually call it V, but I'll just say P7 of R in this case. Okay. What is the dimension of P7 of R? 8, right? So this is 8. All right, so we have the rank of T plus the nullity of T. It adds up to 8, right? So far, so good?
Yeah.
Okay. So this is really going to be the key to the problem. What am I going to want to say next?
Rank.
Go ahead.
Rank.
Did I go?
Solve for the rank, which is.
Okay, the rank of T. Let's talk about the rank of T. So, remind me again, what is the rank of T? Like, what's the definition of it? That's what the range of T is. The range of T, that's the R of T. So, but the rank is, by definition, the dimension of that. So you're totally on the right track. It's just, it's the dimension of R of T, which is the range of the transformation. Remind me again, the range of the transformation, oh, incidentally, the range of the transformation is the span of the transformed basis, right? But one thing I did want to say about that, there was a problem on the homework. A couple of people tried to use this characterization on a set that was not finite dimensional. That becomes a little problematic, so I forget which homework it was, a couple of homeworks ago. But as long as V is finite dimensional, which in this case it is, then there's no problem using that. So we just get this calculation here. So what could we say about that dimension right now? That's relevant for this problem, yeah. You know, we'll come back to that in a second. I just want to stop for a second and say, you know what, so we could try and reverse engineer this, right? And say, well, this is what I want to have happen. I would like the nullity to be at least 2. So if this number, if I want this number to be at least 2, what would I be wanting to say about this number?
Oh, I think she was trying to say that we know that it's at most 6 because the dimension of W is 2 by 3, which means the dimension is 6.
Right, the range of T, you guys I'm sure will remember, the range of T is a subset of the W, which is the codomain. And the null space of T is inside of the P7 of R. We're not going to use that right now, but we're over here. This is a subspace of this, right? So one of the things that we know is that this dimension is at most the dimension of the output space, which is M23 of R, right? Which is, what's the dimension of M23 of R? 6, right? Guys, you don't have to prove those dimensions. You can just cite them if you know the dimension of certain spaces just because they're standard. You don't have to prove them. You just write them down, okay? Okay, good. So the rank is at most 6. So then, so since the rank of T is at most 6, the nullity of T is at least 2 by that boxed equation. Okay, this is the sort of thing that would be very reasonable on a test. It doesn't take that long. It uses important material, right? So just a quick little write-up for that. Okay, you shouldn't be expecting me to give you proofs that take more than, you know, half a page to 2/3 of a page to write down. Okay, just during maybe on the final we'll do that, but not on a shorter midterm. It's just not enough time. Okay. Any questions? By the way, this is really different than like my usual lectures where I'm kind of plowing through the material and stuff. I'm in no rush. We can take our time, ask questions, follow up. Don't be shy. There's probably other people with the same questions you have. So just take our time. It's a lazy Sunday after all, so we can be a little lazy. Kristen?
Do we have to state somewhere that since RT is subset of M2 R?
If you didn't state it, I would be okay with that. I mean, I kind of wrote it here, just very casually. I think that's such a well-known standard thing, I wouldn't be expecting you to say it. During the test, if there's ever anything you're not sure whether a justification is required or not, you can come up and ask me. I probably won't tell you whether what you're asking me about is relevant or not. You're supposed to know whether it actually is something you should be doing or not. But if you want to know if something has to have a proof, I'll probably be the one to tell you that. So. Okay, let's just do one more example, kind of along those lines, kind of get us warmed up here. So another prove type of thing. If T goes from R7 to P2 of R, has nullity equal to 4, then T is on 2. So let's try and prove that. Okay, let's try and prove the T is on 2. Lisa?
So, you can refer to them as nullity there, I guess.
Yeah. Yeah, so does everybody agree this is kind of rank nullity related again? Okay, again, there's a statement about the nullity here. So, for the solution, we don't need a lot of room for this. How might we start this off?
By the rank nullity theorem.
Okay. By rank nullity theorem.
Well, you have to rewrite it again.
Well, but it'll be a different number this
Okay,
time,
so
I
rank
guess.
of T plus nullity of T equals the dimension of R7.
Uh-huh. And what is the dimension of R7?
7.
7.
And we
Let's
also
just go
know
straight
the
to that.
nullity, is 4.
Okay, so this number is equal to 4. Okay, so what do we conclude?
Rank of T is 3.
So the rank of T is 3. Okay, good. So the rank of T, so let me hold on. I want to spread around the excitement here.
Well, we
Nicole
know
looks
that
excited.
in order for it to be onto, our rank of T has to be equal to our W.
Our range of T
Range of
has to be
T.
equal to, rank is a
The
number,
R
the
of
range
T
is the
has to
set.
be equal to
Oh,
the W.
Exactly, so it's good to remind ourselves what onto means. Maybe I'll write that here. I.e., the range of T is all of the output space W. Okay, so we already know that now normally to prove that two sets are equal, you have to show this is a subset of this and this is a subset of this. Normally that's what you have to do. However, it's always true that R of T is contained in W. So this one is a subspace of this one, always, for a transformation. And because of that, now you can start playing a numbers game instead of a set theory game. Does that make sense? If I can show that this dimension is the same as this dimension, and I know half of this equality, namely that this side is a subset of this side, then if I can show that they have the same size, then they must be equal. So you don't really have to prove subsets both ways. And proving subsets both ways would be difficult here because you'd have to pick an element out of W and show that it equals T of something, but I don't even have T in my hands right. I don't even have a formula for capital T. So you wouldn't want to approach it that way, right? So you really want to do it from a numbers perspective. And here's what you want right here, yeah? Because what is the dimension of P2 of R?
3.
It's also 3, right? So these are the same. Okay, but this one, the R of T is a subspace of the P2 of R. Therefore, if they have the same dimensions, they must be equal. Okay, so R of T is equal to P2 of R, and so thus T is onto. All right, so that's kind of a nice little calculation. So just the simple little things like that, likely to be important. Obviously, the rank nullity theorem was a big deal. We really pounded that one, especially the proof of it. So you should very much expect that I may ask you about that. Okay. In general, the more time that I spent on something, probably the more important it is, and the more likely I'm going to ask you about it. I'm going to be asking you about things that are important, and that's going to be more points than things that are not important.
Can you just explain again why we don't have to do the RT as a subset of W and W as a subset of RT?
Sure. So RT is a subset of W always. Just range of T is a subset of capital W. And we could try and prove conversely that every element of W is in the range, but since we have the subset already established, if we can show that they're the same size, the range of T is three-dimensional, the W is three-dimensional, then they must be equal. In other words, you can't have a proper subspace of a bigger subspace that has the same dimension. So if the dimensions are the same, the subspace must be the whole thing. So that's the idea there. Okay, let's try another example. Number 2. I'm going to this time I'm going to be, this is a more specific computational example. Let's let V be M2 of R, and let's let W be equal to P2 of R. Okay? And I'm going to establish bases for both of these spaces. So I'm going to let beta equal the set of 1, 0, 0, 0, comma, 1, 0, 1, 0. So these are not standard bases. These are not standard bases. Then the third one is 1, 0, 1, 1, and the fourth one is 1, 1, 1, 1. Okay? And then we're going to take another basis, I'll call it gamma, for W, which is 1, 1 plus x, and 1 plus x squared. Okay? And these are going to be, let these be bases for V and W respectively. Bases for V and W respectively. Okay, if I give you bases like that, and I just state that they are bases, you don't have to prove it, right? If I give you that information, then don't spend your time proving it. You can just go right ahead and use it. Okay. I feel like I have almost the whole class here, but I have all these papers. Okay, so then here's going to be the question. I guess that's everything. Here's the question. Suppose T goes from V to W, and this is of course linear. It's always going to be linear. But I would state that in the question. I'm just being brief for right now so we don't take notes all day. Has a matrix representation from beta to gamma, which is the following matrix: 1, 0, negative 2, 1, and 2, 1, and 0, and 0, and 2, and negative 2, and negative 1, and 3. And here's the question. Compute T of 1, 4, 0, 6. Okay, everybody's hand tired yet? A lot of information there. But the one thing I didn't give you is a formula for T. Pardon?
Is the one thing we need.
Well, yeah, I didn't give you as much as you think. This problem will take a little work. Lisa?
So we're basically working backwards in this problem.
Backwards.
In that you gave us T, and you have to find a specific.
Okay, exactly. I gave you a matrix representation of T, but I did not tell you what capital T was, right? So I didn't give you the formula for capital T, but you remember from last week that I basically said that this matrix does tell you everything about the transformation. All the information is there. You haven't lost any. Remember we had that, I think we called it B or whatever, and basically it just takes a transformation and spits out a matrix, right? And this is absolutely going to be, I didn't prove it yet, but this is going to be an information preserving correspondence. It's going to be an isomorphism of vector spaces, because this one lived in the m by n matrices, and this one lived in that L of VW space that we were introducing last week, right? And these are gonna be isomorphic spaces, as we haven't proved that yet, but we will. Okay? So, in other words, if I give you this matrix, it's like I gave you this. And of course, if I give you T, then you can do anything. You can calculate anything you want. Okay, so with that sort of background in mind, that reminder, any suggestions on how to, yeah?
Okay, well, we know that the columns of our matrix representation
Mhm.
are associated with some scalars. So can we do it? Because it's like, we have like A times 1, 2, 2, and then plus B, 1, 1, 2, 2. Maybe kind of.
Oh, I see what you mean.
And each of those is,
These are these columns, that's exactly right. You have to remember how the matrix works. These columns are the coefficients of what? Of the outputs of transforming these vectors. So in other words, T of 1, 0, 0, 0 is some quadratic polynomial.
So it's 1 plus 2x plus 2x squared?
Is it 1
Oh,
plus 2x
no,
plus 2x
because now
squared?
we have it- oh.
See, I gave you a different basis here. I didn't give you the if I had given you the standard basis, and this was 1 and x squared, then it would just be 1 plus 2x
So
plus
it's
2x
5
squared.
plus 2.
Laura?
Why are we trying to go back to T? Do we want
Well,
to T?
here's the question we're being asked to find.
Can we just write the coordinate vector for that, for the 1, 4, 0,
Okay.
6, and then multiply the matrices?
Exactly. Okay, so guys, what this question is asking you to do is really to do this diagram. It's forcing you to do that diagram that I showed you last week, right? In other words, start with your vector that you want to input, write down its coordinate vector, then this, okay, so if this is something that you guys, I know we haven't done this a lot yet, and this hasn't been for that long, but it's very important. So the idea is take the coordinate vector, multiply it by the matrix representation. You'll remember that what you get when you do that multiplication is exactly the output of T with respect to gamma. So this thing, I didn't prove this formula yet, but I want you to know this formula. And so then once you know the coordinate vector of T of E, then you can find out what T of E is, right? See, how can I prevent you, if I want to test you on this, how can I prevent you from going straight across? The way I can prevent you from going straight across is I don't give you T. I give you the matrix for you, like I'm trying to prevent you from doing anything. I'm just saying, I'm just trying to show you the power of having this matrix, is that you can still evaluate a transformation by using this diagram. Yeah, go ahead, Lisa.
So the first column, so T of 1, 0, 0, 0 is going to be 1 times 1 plus 2 times 1 plus x plus 2 times 1 plus x squared.
That's correct. So T of, I'll just write down what she just said. T of 1, 0, 0, 0 is 1 times 1 plus 2 times 1 plus x plus 2 times 1 plus x squared. Now we're not going to actually want to go that route with this problem because that's going to take us, it's not that it's wrong, it's just longer. I mean, to get the information we really want to get, we just need to go through this diagram here. Is everybody with me? Okay. Great, so let's try and do the diagram. The first step of the diagram is this part right here. I need the coordinate vector of 1406 relative to this basis. So how am I going to get that?
Oh, do A times that plus B times stuff.
Okay, so I've got to figure out how to write 1406 as A times my first vector, which is 1000, plus B times my second vector, which was 1010, plus C times my third vector, which is 1011, plus D times my last vector, which is 1111. So you have to go through this process, right? And this is actually going to be give us a system of equations. Lisa?
And we put for all A, B, C, D, and
For some
Right?
ABC, for some ABC,
ABC.
we're going to, and which we're going to solve for. Yes. Okay. So what we could say here is we write this equation for some A, B, C, and D, which are elements of the field, and the field is clearly the real numbers in this case. Okay. It's always the real numbers or the complex numbers. If you put capital F here, I'll know what you mean. It's fine. Okay. Alright, so if we look across the matrix, the upper left corner says that 1 is equal to A plus B plus C plus D. The upper right corner says that 4 is equal to D. The lower left corner says that 0 is equal to B plus C plus D. And the lower right corner says that 6 is equal to C plus D. So this is actually not too hard to solve, okay? As you can see, D is equal to 4. So D is 4, therefore C is, okay, by the way, it's actually really, a lot of times people will start solving this by saying, oh, so D is 4, therefore C is 2, they'll do it like that. I would suggest though that you be very careful, because the order in which you write these things, actually you have to keep track of that for this coordinate vector. So I like to put them vertically in the proper order and just start down here. So D is going to be 4, and then C is going to be 2, B will be negative 6, and A is going to equal 1, right? Okay. So my coordinate vector for V with respect to beta is just this column right here. 1, negative 6, 2, and 4. Okay? So we got that. So the next thing in this diagram, before I erase it, is to multiply the matrix that was given by that coordinate vector. Okay? I'm going to erase this here. So now we just take this matrix, 1, 0, negative 2, 1, 2, 1, 0, 0, and 2, negative 2, negative 1, 3. And we're going to multiply it by that column that we just wrote down, 1, negative 6, 2, and 4. Okay? So we just have to multiply matrices together here. 1 plus 0 minus 4 plus 4 is 1. And then 2 minus 6 is negative 4. And then 2 plus 12, which is 14, minus 2 is 12, plus 12 is 24, I believe. Did it right? And this that we just got, that is T of V with respect to gamma. So is my, here's the common thing people do. They get in a rush and they say, okay, so my final answer is 1 minus 4x plus 24x squared. Oops. No problem. 1 minus 4x plus 24x squared, is that right? No, what do I have to do to fix that? So those correspond to, that's the coordinate vector with respect to this basis, right? So my T of V then is 1 times the first basis vector, minus 4 times the second basis vector, and then plus 24 times the third basis vector. Okay, and that gives me 1 minus 4 plus 24 is 21, I believe, minus 4x plus 24x squared. So I believe that should be the right answer. Does that look okay to everybody? All right. Trying to think if there's anything else I could ask you about this transformation. Maybe not for now. I guess that's a pretty good start. Let me give you a slightly more theoretical question that involves this material. We'll go on to number 3 here. Everybody good so far? Oh my gosh, last week was so crazy. So glad this week is going to be, this week is going to be much nicer. Alright, here's number 3. I mean, I've gotten up at 6 o'clock in the morning. I have not gotten up at 6 o'clock in the morning 5 out of 7 days. And as many days of my life as I can remember. But this week I had to do that. It's pretty rough.